Welcome all to the second session of CPP. It's my honor to introduce the first paper for the session, a formalization of the development Closedness Criterion for left linear term rewrite systems by Christina Kohl and Aart Middeldorp. This is a paper that has received a distinguished paper award, so congratulations.
Thank you.
You will receive the certificate for during the business meeting, so we hope to see you there, and then we can congratulate you once again, but of course, yours now.
Okay, thank you. I'm a PhD student at the Department of Computer Science of the University of Innsbruck, and this work I did together with my supervisor, Aart Middeldorp. And the title is maybe quite complicated, but it's a basic result in the area of term rewriting that we formalized in a proof assistant, Isabelle. And it's so the result that we formalized is a confluence criterion, which is called the development closeness criterion, and it works for left linear term rewrite systems. So the outline of my talk is going to be, I first want to give you a small example what term rewriting is, because maybe not everyone knows this. Then I'm going to talk about the result that we formalized, this development closeness criterion, and also about how we formalized this, so how the proof works. And I'm going to talk about proof terms for term rewriting, because we used those proof terms in the formalization. Then, if time permits, I will also talk about how we use this formalization to certify confluence proofs in the tool CeTA. And finally, there's a conclusion. So first off, to term rewriting. As I said, I want to show you an example. So a term rewrite system, or TRS for short, consists of a set of rewrite rules, and each rewrite rule, so in this case we have alpha, beta, gamma, and delta. Each rewrite rule has a left-hand side and a right-hand side. And then the idea is that we do rewriting like this. We look for terms, for subterms, which have exactly the same pattern as the left-hand side of one of our rules. And in this example, the red one is g of a, and this is exactly the left-hand side of the rule gamma. So we can substitute it by the right-hand side of the rule gamma by g of b. More interestingly, if we have variables in our rules, we can substitute other terms for these variables. So for example, the blue stuff here corresponds exactly to the pattern of the rule alpha. And the x has been instantiated with g of a. The y has been instantiated also with g of a. And if we now want to do rewriting, we go to the right-hand side of the rule alpha and use the same substitution for x again. So this g of a here and g of a here. So that's a very simple idea, but it's still very powerful. It's actually Turing complete. So term rewriting is a Turing complete model of computation. Now the property that I'm interested in my research is confluence. And I formalized this confluence criterion. So we should talk about what confluence is. It's basically the picture here on the right. And the idea is that when you can rewrite a term in two different ways, so you start here with some term, which is just symbolized by a dot, and there are two options of rewriting, then you can find a common reduct again. So you can join to the same term again. If a term rewrite system has this property that you can always draw diagrams like these, then it is confluent. And the nice thing about this is that it guarantees unique normal forms of the term rewrite system. A normal form is something where you can't do any more rewriting, where no rewrite rule applies, and we are generally interested in the normal forms of a term rewrite system, so it's good to know that we have unique normal forms. Unfortunately, this is undecidable in general, so there's no algorithm to tell us for every term rewrite system whether it's confluent or not, but there exist many criteria for subclasses of term rewrite systems, and many of these are based on critical pairs. Also, the one that I formalized in the proof assistant, Isabelle, the development closeness theorem, is based on critical pairs. So I'm going to show you the definition of critical pair. Looks a bit complicated, but that doesn't really matter for now, I think. Just the idea behind this is that we have two rules which have an overlap. So we look at the left-hand sides of our rule, and if there are function symbols that appear in both of these rules, then there's sometimes an overlap, and we have a term which can be rewritten in two different ways, either using one of the rules or the other one. And this construct here, So in general, this is then a peak, and then there are additional conditions, the ones here, which make it a critical peak. And we are, so for confluence, we are always interested in these critical peaks. I think it doesn't serve to go through all of these criteria, but yeah, just for the terminology, this thing is the critical peak, and then the two different terms here at the bottom, these are the critical pair. And we're just going to look at an example of how this works for the term rewrite system of the original example. So here, for example, we have the F appearing in alpha and appearing in beta. And then we have a critical peak, which looks like this. This term can be rewritten either using beta here on the left or alpha here on the right. And the order actually matters. So we always do the step at the root on the right and the inner step on the left. Yeah, so this would be one critical peak of the system. There are two more because there's the G of A in rule gamma, and the G also appears here in alpha and here in beta. So there are two more critical peaks. Now I can explain the result that we formalized, the development closeness theorem. And it was first stated by Vincent van Oostrom in 1995, and there's a journal paper also from 1997. And it says that if a term rewrite system is left linear means that on the left we don't have duplicate variables, so the left-hand side of our rules don't have duplicate variables. And we look at all critical pairs of our system and check that they can be closed by a multi-step. So this arrow with the circle is a multi-step. So if these two conditions are fulfilled, then we know that the TRS is confluent. And this is a really nice criterion because it's easy to automate. It's easy to put into a tool for deciding confluence because the critical pairs are actually easy to compute. And there are only finitely many if your term rewrite system is finite. So it's easy to write down an algorithm which simply tries to find out whether this criterion holds. And this has been used for many years in tools for confluence. This was, so Vincent van Oostrom was interested in this because he was interested in higher order rewriting. So this result actually works for higher order rewriting, but we didn't formalize the higher order case, only the first order case. And then, yeah, the multi-step is also called development step, so that's where the name actually comes from. And now the idea for our formalization was to not work with multi-steps directly, but use proof terms for term rewriting instead. Proof terms were also invented by Vincent van Oostrom together with Roel de Vrijer. And the idea is that every multi-step can be represented as a proof term, and every proof term corresponds exactly to one multi-step via this relation. So the source of the proof term is exactly S, and the target is exactly T for a multi-step from S to T. And how this works, we can again look at an example. So proof terms are just first-order terms built from function symbols and variables as usual. But now in addition, we add rule symbols, which are in our case these Greek letters here. So alpha, beta, gamma, delta are rule symbols. And they are used like function symbols. So they have an arity, and then you have arguments, the number of, so the arity is the number of arguments. And for example, this rule symbol alpha here has two variables on its left-hand side, the x and the y. So the arity of alpha is 2. And this looks then, for example, like this. So here we have an example of a proof term, alpha of gamma and g of a. Now, if you want to go from the proof term representation to the multi-step, we compute the source of this proof term by looking at the left-hand side of the rule symbols. So the left-hand side of alpha is this one. So I marked this in red here. And then the two arguments are the things we have to put into the substitution for x and y. So gamma, again, we look at the left-hand side of gamma, so g of a, and we put it in here at the position of x. And then g of a, we compute the source of g of a, but the source of a normal term is just the term itself, and it gets put into the position of y, so in here. Then for the target, we do almost the same thing, but we look at the right-hand sides of all the rules. So we look at the right-hand side of alpha, which is again the red thing, and then at the right-hand side of gamma, the g of b, and the variable x appears here and here, so g of b appears here and here. And this was quite useful for the formalization, because now we are dealing with first order terms, and there are lots of already formalized results about first order terms in our library in Isabelle. For example, stuff like context, substitution, positions, and we could reuse all of that for the formalization. That was quite useful. So, and to see an example of how this criterion applies, of course, I chose a term rewrite system, which is development closed for my main example here. So in this case, you would first check that all the rewrite rules are left linear, and they are, because there's no duplication on the left-hand side. And then you check that these three critical pairs are development closed. So there should be a multi-step between each of these going from left to right, so the order matters. And yeah, can be done for the system. So this is confluent by the development closeness theorem. Okay, so the proof of this result is based, so Vincent van Oostrom in his paper already presented a proof, and our formalization follows mostly Vincent's proof, but we had to plug in, of course, a lot more details. And the only difference is then that we used proof terms here for the multi-steps. The idea of the proof is to show diamond property of the multi-step relation, and this then immediately implies confluence of the term rewrite system. The diamond property is the thing here displayed on the right. You start by looking at two multi-steps from the same term, so from S to T, from S to U, and then you have to show that there exists a multi-step from T and one multi-step from U, which both go to the same term. So that's our goal here. And we do this, first we represent the multi-steps as proof terms, then we use induction on the amount of overlap between the two proof terms. So this function, this solid black triangle, is a function that computes the amount of overlap. I won't show you the definition of that function here, but you have a question? No, every parallel step is a multi-step, but not every multi-step is a parallel step. So it's more powerful, kind of. No, it's so you can do nested steps in multi-steps, but you can't. So you can't do arbitrary steps. You can combine arbitrary steps into one single step, but certain steps can be combined. So it's everything which you could possibly do simultaneously, you do simultaneously. But some things can't be done simultaneously. Sometimes you have to do one thing before the other thing. Okay. Okay. So now again, this, so we were at the amount of overlap. This can be computed by simply labeling the sources of the terms and then counting where labels overlap, and this gives us this function here. And now, since we do induction, we first look at the base case, which is that we have no overlap, and this can be handled quite nicely by residuals. And these were also introduced by Van Oostrom for proof terms. So this is this definition here. Note that it's a partial definition, so the residual operation is not defined for arbitrary proof terms. It's only defined if they are orthogonal, actually. So if they have to fulfill certain properties, there shouldn't be any overlap. But so maybe an example of when they are not defined would be if we have rule symbol alpha on the left and then a different rule symbol on the right. This would be covered by none of these cases here, and then the operation is simply undefined. So these 5 cases written down here don't cover everything, and all the cases, all the cases which are not written down are just undefined. Now we have these nice properties that if there is no overlap between two proof terms, then the residual operation in both directions is well defined, and the target of this B after A and A after B is actually the same term. And now you see that this looks exactly like what we want to show here. So we can simply plug in the residuals here, and we are done with the base case of the proof. Now for the step case, this is really interesting. So now we do have some overlaps, and we denote this by these colored triangles here. So we have a blue blue multi-step consists only of this one blue triangle going to the right, and then we have several different steps denoted by red triangles here on the left. And now we pick an innermost. I forgot to say they do overlap at some positions, because so in the picture you see that there are 3 positions where there's overlap. And now we pick an innermost of these overlaps. So in the example, we could actually pick the left or the right one here, but not the one at the top. That wouldn't be innermost. So we pick an innermost one, and then we extract the corresponding critical pair, because each overlap corresponds to one critical pair of our underlying rewrite system. And we need to extract the critical pair to be able to apply our assumption. The assumption was that in our rewrite system, every critical pair is closed by a multi-step, and we want to use that assumption. So we first need to compute the critical pair, then we can apply the assumption, and we get this step here in the picture, the step D. But D is not enough here. What we actually want is a step going from this intermediate term T prime to U. Because the idea is we want to apply the induction hypothesis to close this diagram here. So we need a step. So this step here and this step here could work to close the diagram if we could show that, well, this thing actually exists and is well defined, and the amount of overlap is less than between the original terms. So if we have less overlap, we can apply the induction hypothesis. So one challenge was to show that this is well defined, and we did this. So there appear several operations here, which are also operations on proof terms. And the definition is quite similar to the residual operation. The deletion simply removes the redexes of one proof term from the other one. And it's also a partial operation, because if the redexes of the term on the right are not appearing on the left, then it's not defined. And then the other one is the join operation. It simply combines 2 proof terms into one, but that's also not always possible. Then we used these nice results about these operations, about the join, residual, and deletion, to show that this term is well defined. So this was something that we actually came up with. So these operations were already mentioned by Vincent van Oostrom in Therese, for example, but not this result. So this is something that we actually had to come up with ourselves. Now we use this to show that this step exists, and then the final step of the proof is to show that the amount of overlap decreases. And this was, I would say, the hardest step, and was just an exhaustive and exhausting case analysis on positions. But we managed it, and it was crucial to select an innermost overlap in the beginning, because otherwise actually the amount of overlap here could become more, because you could have duplicating rules which duplicate redexes. So this is the point where innermost is really important. Okay, so then we could close the proof by our induction hypothesis, and we are done. Briefly want to talk about the certification stuff. So we included this result in the ISA4 library, which is being developed in Innsbruck. And this ISA4 library we use the code generation feature of Isabelle to obtain the tool CeTA. CeTA stands for Certified Tool Assertions. And CeTA is then able to verify certificates. Certificates are something that normal confluence tools should produce. So you would put a TRS into your confluence tool. For example, you could use the tool CSI. And then CSI should produce a yes or no answer together with a certificate of why it thinks yes or no. And then CeTA could verify that certificate. And we basically made CeTA more powerful by adding this development closeness criterion. So to conclude, we formalized some theory about proof terms in Isabelle. We also extended the existing library with this development closeness criterion, and we obtained the extended certification. This took about 10,000 lines of Isabelle code, so quite a lot. And there's some future work or current work, actually this item is done by now. So the almost development closeness is an extension. And I managed to also formalize the extension by now. And more interesting work would be commutation with relative termination, and this relative new paper by Hirokawa, Nagelevan, Oostrom, and Oyamaguchi, which also extends the development closeness criterion. Yep, that's it. Thanks.
Thank you for the talk. I would like to remind that those attending online, you can also ask questions via AirMeet, and then they will be read out by our student volunteers. So, any questions? We have time for some.
So, if I understand well, the amount of overlap that is described only by a natural number?
Mm-hmm, yes.
And you never need anything better than that?
No. It's just you count the symbol. So we look at two multi-steps starting from the same source. And then we look at which function symbols are changed or which function symbols are redexes in the one step and in the other one. And then we look at which of them appear in both, add them up, and that's your number, your natural number.
So with this new kind of observation of these algebraic properties, I'm always obsessed with these synthetic proofs where you just have axioms, and then your rewrite system is just, abstract. It's just points, rewrite to points. Mm-hmm. Can you imagine a synthetic proof for this result?
Okay, so let's back up. You mean that result?
That's the tool. I wonder if you can imagine synthetically stating and proving the whole theorem, the development closeness.
I don't quite see what the difference is to what we are doing now. So what do you mean exactly?
So what I feel is that synthetic proof is you don't have terms, you have abstract things. You have certain operations on them, which might be some abstract overlap operation.
Okay, now I get it.
You have certain algebraic properties, and then you prove some theorem about that. And you say, hey, look at terms. They happen to have all these structures on them. Therefore, we can just apply this as lemma.
Okay, yeah, might be possible. So right now, I'm actually relying a lot on this first order term structure and then context, substitution, positions, all of that. And I'm actually not sure. So positions really play a key role here. And that, I think, would be the challenge when you want to abstract from that, how to deal with the positions.
Okay, let's thank Christina once more for the talk.